Hello, and it's the C2 Walking Talking mock today from 2014, and as usual it starts with a fairly nice question that we should be able to get some marks on. So we've got a label, okay, and it shows the ingredients in a drink called cola. We've got several ingredients here, worth just looking through them. In terms of science, this is probably going to be the one we're interested in because of the word at the end. It says the pH of carbonated water is 4.5. Okay, so that is 4.5. So we've got to study this. And the pH of cola is 2.9. Got like that. Name the ingredient on the label that lowers the pH of cola to 2.9. Well, we've only got one thing that's going to be acidic to lower the pH. Much harder question now then, except it's not really hard. What it requires is good recall. Okay, so it says which ion causes the pH to be 2.9. Now ions, remember, have charges, either positive or minus, and we've got to think of an ion. Now there are two we need to know that cause something to be acid or something to be alkaline. I'll give you the one that's alkaline. All alkalis contain that. So we need to figure out which one the acidic one is. Okay, almost like the opposite one. And remember, together, whatever that acidic one is, plus the alkali hydroxide ion, make water. Because that's our neutralization equation. Part B. A student investigated the food colouring in cola in a fruit drunk using paper chromatography. Yep, nice, straightforward. Says the start line, which is here, should be drawn with a ruler, and I think it's pretty obvious. We've always done it in class. Okay, we always use the same piece of equipment. We never use pen. Okay, and we've got to try and say why we wouldn't use pen. So we've got to be thinking here, why don't we use pen? What would be the problem if we run paper chromatography using pen? Okay, so you'll have to figure out what that is. Now this is a really nice question. It suggests 3 conclusions you can make from the student's results if you can interpret a chromatogram. Okay, so we look up 3 conclusions, and for that really we've got to be comparing. So I'd be looking at this one. And what can we say about that? Well, it looks like they both contain about this one. We're looking at this one and this one and this one. Well, they each contain one unique, and then I'd be looking up as well at the total. So how many colours does cola contain? How many colours does fruit drink contain? So we're just trying to make as many comparisons as possible, saying essentially what they have in common and what's different, and perhaps looking at totals. So we're using a lot of data, and it should be fairly straightforward to get 3 marks, although potentially a lot of students might not. Then we get to kind of the harder end of the chromatography question. Okay, so this question, 1C, is about separating caffeine in gas chromatography. It says, why do different compounds separate in a gas chromatography column? Again, I say it's hard, but it's straightforward recall. Okay, so in a gas chromatography column, got something like this, they'll go around, and then there'll be a detector, and it will give peaks, something like that. Now you've got to say why they move through this at different rates, and that's literally what we have to refer to. I'd be referring to the speed or the rate at which they move. Okay, next one. only one of the questions in the table can be answered by science alone. Now, these questions often compare science versus social. Okay, so if we look at the first one, should caffeine be an ingredient in drinks? Now we've got to think, who should decide that? Should it be scientists? Probably not. It should probably be, I don't know, a government. Because scientists can provide the evidence, but they shouldn't really say what to do with that evidence necessarily. That's for other people to determine. Is there caffeine in a certain brand of drink? Well, yes, scientists can say that. We can tell you if there is or not. And how much caffeine should people drink? Again, okay, that will be determined by government. Okay, they'd be looking into that. They'd determine how much caffeine people should drink. And then give two other reasons why the other questions cannot be answered by science alone. Well, for that, we'd maybe be talking about it being some kind of ethical issue or a social issue. I think these are probably more social issue. I'd maybe be thinking about experiments as well. Scientists can do experiments. Can we therefore do an experiment to say should caffeine be an ingredient used in a drink? No, we can't. We can say if it is or not. We can say the effect if people drink it, but we can't say should it be in. Okay, that's something for someone else to decide. It's an opinion. Scientists don't deal with opinions. Right, and so we come to the sixth marker, which I think we've looked at before. So this one, we're looking at chlorine. Cl2 is a gas at room temperature, but sodium chloride is a solid at room temperature. And it even gives us a nice little diagram. So, as always with these, I do a little spider diagram. So we've got chlorine. Okay, it's molecular. It's think about the typing of bonding. It's a simple covalent structure. Okay. Between the molecules, so if we've got one here and another one here, there's not much holding it together apart from these things which we called weak intermolecular forces. And linking it to that, there's not much energy needed to overcome those forces so they can move apart. Looking at sodium chloride, now we've got ionic bonding, we've got strong electrostatic forces, and we've got to refer to it in those terms between the negative chlorides and the positive sodium ions. Lots of energy needed to overcome it, and instead of being a simple molecular structure, you can talk about being a giant ionic structure. Okay, it's actually relatively straightforward, but you do have to know about your structure and bonding. And remember, with those questions, you've got to be thinking about your English as well. Next one, question 3. Okay. Well, we've got a balancing equation. Now, it's actually quite nice. It's worth 2 marks. Okay, so you're thinking I'm probably going to have to do a bit of this, and there is indeed a bit of it to do. Okay, so from the diagram, it says sulfur dioxide produces sulfur trioxide with oxygen. So the first thing I do is put in our oxygen down here. A lot of people will just write O on its own, and you've got to think why that is wrong. Then what you should do, dash your line, okay, and count up the number of atoms of each type you've got on each side. So you'd count up the number of atoms of S, the number of atoms of O, number of atoms of S, number of atoms of O, and you can only balance, that's where we balance on these lines. Okay, so 2 marks should be two fairly easy marks. Next one, 3b, part 1. The pressure of the reacting gases was increased. State the effect of increasing the pressure. So now this is important. State the effect. So firstly, I'd be saying, does it increase the rate of reaction, or does it decrease the rate of reaction? Okay, and then the second part of the question, it's almost like a two-parter. Explain your answer in terms of particles. So at that point, I'll be going on to explain it in terms of particle theory. Now, what we've got to think is, if I look here, sorry, just ignore that one I've just drawn. If I look here, and this is at standard pressure, we've got 5 gas particles, and they're moving about randomly. And then we increase the pressure, so that means we're probably going to lower the volume. So we've got the same 5 gas particles. Which one is going to be reacting the fastest? Okay, is it going to be lower pressure? Higher pressure. Ignore that. Or lower. Now, when we're explaining answers in terms of particles, we have got to talk about collision theory. It's this idea that particles only react when they successfully collide. So we'd be making a comment on collision theory, and would also be saying why. And for this, I'd be comparing the space and the likelihood of collision occurring. Uh, 3b part 2 is about catalysts. To use reaction, the gas passes through a layer containing pieces of the catalyst, and we've got 2 catalysts, we've got A and B. And it says, suggest and explain why shape B is more effective as a catalyst than shape A. And looking at the shape, if we draw around this, okay, just drawing around the cross section, not much. And compared to that, I think we've got to be talking about surface area, and then linking surface area to the reaction. Okay. And then again, straightforward recall. Reaction is carried out at a high temperature to provide the reactions with the activation energy. What is meant by activation energy? And we draw diagrams before that look something like this, or indeed, like that. Okay, this is what we've always called the activation energy, but we've got to explain what it is, and this is straightforward recall, and it is the energy, the minimum amount of energy the particles need in order to start the reaction. Okay, continuing this question. Sulfuric acid reacts with metals to produce salts. A student concluded that potassium would not be a suitable metal to react with sulfuric acid. Well, yep, they're perfectly right. Okay, so potassium is definitely not a suitable metal. Okay, and we've got to explain why. So we've seen the reaction with potassium with water. It's gone in there. Okay, it's been very violent, and that's probably a good word to use. So we want to explain why that wouldn't be a good idea. Okay. a student reacted zinc metal with sulfuric acid to produce a salt and another product to complete the equation for this reaction. Okay, so we know that metal plus acid goes to salt and hydrogen. Okay, because this is a metal on its own. So, if you want to write in the formula for hydrogen, you definitely wouldn't be writing H on its own, okay, because it's a gas, or it's a particular type of gas. And then we're going to write our salt. Now the salt is the metal combined with part of the acid. Okay, so I'd write that in, and then I'd double check that everything is balanced. It looks like it would be, and it doesn't ask us to balance it, so we're probably okay. The student wants to increase the rate of reaction between the zinc and sulfuric acid. State one other way other than using catalysts that the student could increase the rate of reaction. Well, we've got a number of ways. Okay, pressure's probably not going to work in this case because it's liquids, so we think about maybe temperature. We're thinking about maybe the surface area of the zinc. Okay, and those should be pretty straightforward to get. Question 4 is an electrolysis question. Always pretty tricky electrolysis questions. So it's worth spending a bit of time on this one. So it's about zinc and magnesium. Zinc is produced by the electrolysis of molten zinc chloride. Okay, right. So now, when it says molten zinc chloride, you wouldn't have studied molten zinc chloride at all. What you will have studied is aluminium oxide, and that's a molten one as well. And that is a real key word, is molten. Because molten means melted. It's not dissolved, and therefore we're not going to be talking, at least for this initial part of the question, about other ions being in there. So sometimes we say if it's in solution there's other ions. There won't be in this case. Why must zinc chloride be molten for electrolysis? Okay, again, that keyword molten. Okay, well, why can't it just be solid? And if it was solid, could anything happen? If I draw a zinc chloride, that's roughly what it'd look like. Maybe with more negatives, but it doesn't really matter. So we've got to say why that wouldn't work and why it does need to be molten. Question 3, describe what happens at the negative electrode. Okay, so we've got zinc chloride. Now, first thing I would be going to here is my data sheet. Because if I don't know a lot about zinc chloride, I want to find out what ions are in zinc chloride. And if I have a look on my data sheet, which you get in your exam, I find they are this. So now I know which one's positive and which one's negative, just in case I didn't know before. So if it's the negative electrode, well, my positive ion is going to be moving there. So I'll be talking about Zn2 plus moving to the electrode. I would be talking about gain or loss of electrons. I definitely tell them how many electrons, and it's always crucial to state with these metals that it forms atoms at the end. So instead of it being zinc ions, it's zinc atoms. But you've got to judge how many electrons. I mean, I think technically Yeah, technically you could just write the half equation. So what happens is zinc gains 2 electrons to become zinc arms. I mean, that summarises it completely. It might not be worth taking the full gamble on that, but I would if I knew it. Complete the half equation for reaction at the positive electrode. I'll go through this one rather than get you to try and work it out. Okay, so we're forming chlorine molecule. Okay, so that means initially we would have had chloride ions starting off, and each chloride ion, okay, we need 2 of them to get our 2 chlorine atoms to form a molecule. So we do this. Now each chloride ion, which I'll just highlight, that's the chloride ion, they need to lose 1 electron each, because overall they have a negative charge. Electrons have a negative charge. And because there's 2 chloride ions, we need to lose 2 electrons. Onto 4b, bit of a change in direction. Magnesium can produce from magnesium oxide. The equation for the reaction is, and then we've got silicon plus magnesium oxide goes to silicon dioxide and magnesium. Quite a tricky one now. How can you tell from the equation that a reaction is done at high temperature? Now I'd be looking at this, and the thing I'd spot is I'd look for anything that doesn't look quite normal, and that's the thing that doesn't look quite normal. That magnesium becomes a gas, and you've got to think, why would magnesium become a gas? It says it's endothermic. Okay, so what is meant by an endothermic reaction? And I'd be talking about a reaction that either takes in or gives out energy to or from the surroundings. And if you think about the alternative, we've got exothermic, and X is associated with exits, that kind of thing. Next one, accompany you made magnesium using this reaction. Calculate the mass of magnesium oxide to produce 1.2 tons of magnesium. Right. 3-mark question. Always tricky. This is reacting masses question. So, I think the first thing to do is to probably... Actually, it tells us in the question, yeah. So, calculate the mass of magnesium oxide to produce 1.2 tons of magnesium, and it does give us the relative atomic masses. So the first thing I'm going to do is just check my equation. Okay, so it's up here, and you see we've got 2 magnesium oxide, 2 moles of it, giving 2 moles of magnesium. So essentially we've got this. Okay, so first thing I'm going to do is work out the relative atomic masses of both these things. So magnesium, it's 24, oxygen's 12, equals 36. However, there's 2 moles, so we get a total of 72. I'll just move down a moment. Other one, 2 magnesium, magnesium's 24, times 2 equals 48. So essentially, 72 grams or tons of magnesium oxide would give 48 tons of magnesium. Thing is, we're looking for what mass would need to produce 1.2 tons of magnesium. So what we'll do is I want to find out this one, and I know this one. So if I divide both sides by 48, that'll give me what 1 ton would make. Again, just move down a bit. So 48 divided by 48, so 1 ton would be made from 72 over 48. Don't have a calculator, so just have to work that out. And then what we'll do is we'll times it up to get our 1.2 tons. So again, what we do to one side, we've got to do to the other. So it would be 1.2 times 72 over 48 would be our answer. And I realise I've just gone horribly wrong, because earlier on in the question I said that the atomic mass of oxygen was 12 when in fact it's 16. So I don't know quite what I was doing there. So instead of it being 24 plus 6, 24 plus 12, it would be 24 plus 16. I was wondering why it didn't equal 40. So instead it would be 40. This would be 80, 80, and 80. Horrendous error, but we should actually get the right answer. It's worth noting that calculating the atomic mass of both those things, even if you're not sure about anything else, is worth quite a few marks. It's also worth noting that you do need to refer back to the equation in questions like this, reacting masses ones, and you're always trying to get the thing you already know, which is this 1.2 tons of magnesium, down to 1. Okay, so dividing by itself. Sorry for the mistake. Next one. Company calculated that it would produce 1.2 tons of magnesium. Yeah, but only 0.9 tons was produced. So, as always in science, we can't produce 100%. So, nice easy one. And then to get in the percentage. Give one reason why the calculated yield of magnesium might not be obtained. So we've got to think what might happen in the reaction for us not to get however much we were expecting. So we might be talking about things like it potentially being a reversible reaction, some of the reactants getting lost, or some of the products getting lost, okay, during the process. And then a really weird question, okay, because this doesn't come up often, nanotubules. It is in the spec, okay, but nanotubes, very rare. Okay, so it says carbon atoms are used to make nanotubes, and then we've got a diagram. It says carbon atoms in the nanotube are bonded like a single layer of graphite, and that's our way in, because we should really know the bonding in graphite. And it even shows us a bit of that single layer of graphite, so we can see, you know, from what we know, every carbon is bonded to 1, 2, 3 others, and we get this hexagonal arrangement. And it says, suggest why carbon nanotubes are used as lubricants. And they're often really tough questions. These suggest questions are usually the hardest ones, I think. Okay, so think about lubricants. They allow things to slide over each other without causing friction. So what we can say is maybe these nanotubules can just slide over each other, okay, easily. And the reason for that would be because there's actually no bonds between the nanotubes. It would only be weak intermolecular forces, just like in graphite. That's a layer of graphite. Terrible layer. And this is another layer. There are only weak intermolecular forces. Sorry, these are supposed to be dashed lines. Between the layers, so there would only be weak intermolecular forces between these nanotubes. Tough question. I'd imagine people didn't do well on that one. Next one, explain why graphite can conduct electricity. And if we're talking about conducting electricity, we have got to be talking about electrons. and in particular those electrons that can move. Okay, so we've got to be talking about movement of electrons and this particular type of electron. Okay, and then we get to magnesium oxide nanoparticles can kill bacteria, so another nano question. They can kill bacteria, okay, right, fine. It shows the percentage of bacteria killed by different size nanoparticles. Right, okay, so we've got two types, type 1 and type 2. Type 1 and then type 1 is the blue, type 2 is in red. Give two conclusions that can be made from figure 6. Right, so looking at the red one, this is the percentage of bacteria killed, so highest is best. So type 2 bacteria, well, we can say fewer type 2 bacteria killed. Okay, more for type 1. And then I'd compare probably the shape of those two lines. So we can say type 1, type 1 is what we call linear. Okay, and type 2 is non-linear. Could maybe use a point, so this one, so a certain size, this looks like 8. So that's 100% being killed. Okay, and it looks like the other bacteria is also killed around about 7.5. So by the looks of things. Okay, so we'd have quite a few comments to make. Points are plotted for only some size of nanoparticles. So next question, sorry. Points are plotted for only some size of nanoparticles. Would collecting and plotting for data for more sizes of nanoparticles improve the conclusions? Well, I'm always of the opinion that more is generally better. So I'd probably say, well, you could argue either, but I'd probably say you could see the pattern more clearly or confirm the pattern. Okay. Alternatively, you could say, well, the pattern already looks quite clear. We can already see this non-linear pattern, this linear pattern. So you could say, well, it's already clear. I mean, generally, I think 4 points is far too few to plot a curve or a line of best fit and to be confident in it. So I'd probably say more data to try and confirm the trend. Right, 6b is an absolutely lovely question. Should really get 4 marks on this. So magnesium oxide contains magnesium ions and oxide ions. It does. Describe as full as you can what happens when magnesium atoms react with oxygen atoms to produce magnesium oxide. If I was going to brainstorm this, which I would because it's significant above marks, I'd be definitely talking about electrons. I'd be definitely talking about the movement of electrons. I'd definitely talking about from where, from like which atom to which atom, from something to something. And finally, I'd be talking about the purpose. So I'd be talking about this idea of a full outer shell. No real excuse to get fewer marks. Question 7 then. This glass is made from silicon dioxide. So, silicon dioxide, SiO2. Not that you need to know that. Silicon dioxide has a very high melting point. It does. Other substances are added to silicon dioxide to make glass. Glass melts at a lower temperature than silicon dioxide. Suggest why? Well, we could just say the other substances. I mean, personally, I'd say something like the other substances have lower melting points, but we could say, if we wanted to, the idea of bonding, we'd talk about weak bonds. Or I'd probably talk about this idea of it disrupting the lattice, much like an alloy. Okay, when we're talking about melting point, we're often talking about bonding. I think it's worth making that clear. Sodium oxide is one of the next question. Sodium oxide is one of the substances added to silicon dioxide to make glass. It contains Na+ ions and O2- ions. Give the formula of sodium oxide. So we form a compound. This compound has no overall charge. So we've got Na+, O2-. Well, we actually need two of these to balance out the double charge, the double negative charge, okay? And then we just write the formulas in the same way we'd write maybe CO2, but not the same way. Next one, sodium oxide is made by heating sodium metal in oxygen gas. Complete the diagram to show the outer electrons in an oxygen molecule, O2. I'd probably be tempted to draw a dot and cross here. Okay, makes more sense. So, key thing, very key thing, outer electrons only. That's what we usually do with these covalent bonds. I'd look in the periodic table, which you get given, and you'll find that oxygen is in group 6. So each atom of oxygen has 6 electrons in its outer shell. So if I just tried drawing them in, we'd probably find that it didn't have enough. And the principle is, with these, is the share them. So if I was drawing, say, hydrogen, which has 1 electron in its outer shell, it would put both. Each one will put 1 electron into the middle. Okay. You've got to make sure, and this is the key thing to check once you've done it, is that none of the atoms, none of these oxygen atoms, have donated more than 6 electrons, have used more than 6 electrons, so double check that. And final question, glass can be coloured using tiny particles of gold. Gold is a metal. Describe the structure of a metal. So, nice straightforward question to answer. Describe the structure of a metal. So, if you're going to draw a metal, view through it, would see particles together, except we wouldn't call them particles, we'll call them something else. Okay. Now these particles, or atoms we should call them, I don't know why I'm using the word particles, lose their electrons, or they lose some, they become what we call free electrons, or delocalized. And that leaves the metal atoms actually charged, so they're metal ions. So essentially all we need to talk about is that these are closely packed, okay, metal ions, and there are delocalized electrons. There's nothing more to that question, really straightforward. And I think that's it for the C2 paper. We always check there are no questions. Okay, brilliant.